Hello everyone. Hope you guys are doing very good. So remember in a couple of weeks back, there was one student who raised this question that is it possible that you solve a few sample problems in class so that students feel confident addressing any kind of problems? And I said over there that yes, we can do that. And this particular session is specially arranged to answer that query by the students. So what we're going to do is to use the kinematic analysis principle that we have already covered in much detail previously. We have done the position analysis, then we did the velocity analysis, and then the acceleration analysis was done in much detail. So today is the time when we're going to apply those principles to solve a few problems. So when I wanted to kind of plan this whole activity, I thought about uh, uh, try to solve a few problems given in the end of the chapter. Uh, but then I stopped myself and I said that let's kind of get out of that circle, get out of those shackles and try to identify two different problems. And this is exactly what we have done over here. So these are the two problems which are a bit different from the problems given in the book. So this is going to give you a wider horizon to address similar problems. So I would advise that you have to solve the end problems. But in addition to that, this particular session is going to give you the further assurance and further ideas to solve similar problems. So let's start the discussion. So the very first problem that we are going to discuss corresponds to car lift mechanism. And in that, you can see that there is this hydraulic actuator, which when extends, it forces the car to be lifted upwards. And we are going to try to solve it mainly for differential kinematics. And for that, we have to consider the vector loop equations. These vector loop equations, remember, we have already solved for a few problems, so that would not be a big issue for us. So that is what we're going to start with. Once the vector loop equation has been found out, we're going to use that to solve this problem, which says that the hydraulic actuator extends with the velocity s dot, which is, by the way, over here, s dot. And for that particular scenario, find the rate with which, or in other words, the velocity with which the car is being lifted upwards. So that is going to be corresponding to this velocity h dot. And once we have found out the generic expressions for those, we're going to determine for some specific values. For example, when s dot is 1 meters per second, or in other words, the hydraulic actuator is being extended with a velocity of 1 meter per second. So we're going to see that what is going to be corresponding h dot when the theta, which is right over here, is equal to 30 degrees. So this is going to be a specific case, but before we discuss this specific case, we're going to derive the generic equations which are going to be used for this purpose. And in addition to that, some sense of dimensions should also be in front of us, and for that we would identify that this length L is actually equal to 2b, which b is from this to this, as well as from this point to this point. So this length L is actually equal to 2b, and 1b is actually equal to, in this particular case, 1 meter. And that is only going to be effective when we're going to discuss the specific case. But just before that, we're going to find out in step number 2 the generic expressions, so we can plug in any values for L or B in that case. So let's prepare the problem. So the very first thing that we generally do is to define the axes. And in this particular case, we are going to say that the axes are originated at point A over here. The x-axis drawn in dashed line over here is going to take this shape. So this is x-axis. Orthogonal to this x-axis, you are going to have the y-axis. Now this point A is already known. The other points are going to be point B over here, point C where the linear actuator, hydraulic actuator is connected with the lifting platform, and then you have another point right over here which is defined as point D. So these are the important points to be considered. Now the next step is going to be to define the vectors in this particular case. So let me use a different color. So the very first vector is going to start from point A, go all the way horizontally to point B, and that would look something like this. So this is a vector starting from A, going all the way to point B. Another vector is from point B all the way to point C. This is going to be encapsulating the movement of the hydraulic actuator, and this is going to be over here. The third vector starts from point A, the origin of the frame, the global frame, and it is going to go all the way to point C. So this would look something like this. So you have, in that sense, a triangle available to you. And let me quickly draw this triangle over here so that we can have a clear view of it. So you have the horizontal vector L, you have another vector S, and you have the vector B over here. So this is point A, this is point C, this is point B, and you can readily see that when you add vector L with vector S, you find vector B. So we can write down over here for triangle A, B, C, and using the vector loop equation, you can write down this expression like B is equal to L plus S. And since these are vectors, let me indicate that as well for clarity. Now once you have this vector loop equation, you can use the polar notation to write down a better expression over here. That is going to be something like B e raised to power j some angle. And this angle is corresponding to vector B, so this is going to be right over here. So this is the theta. So BE raised to power j theta to be equal to L e raised to power j theta corresponding to L, which is equal to 0. So I'm going to write down over here the corresponding theta 1 is equal to 0 for length L. And then you have to add this with S e raised to power j theta corresponding to S, and that is going to look something like this. This is going to be theta S, or on the mechanism as well I can identify theta S over here. So this is going to be S e raised to power j theta S. So this is the vector loop equation defined in the polar form, and now you can use the Euler notation to construct the two equations corresponding to real and imaginary axis. So for real, you are going to write down something like this, like you have B cos of theta over here to be equal to L cos of theta 1, which is actually equal to 0, so that would turn this cos of 0 to be equal to 1, plus S cos of theta S. So since theta 1 is equal to 0, so this is going to be equal to 1. So for that reason, I can write down to be equal to L uh, plus S cos of theta S as the expression corresponding to B cos of theta. So label this one as number 1, and you have the imaginary axis once again, the expression corresponding to imaginary part written down. So this is going to be something like you have B, uh, this would imply that B sine of theta to be equal to L sine of theta 1 to be equal to 0 in this case, plus S cos of theta S, sorry, sine of theta S. Now, since this expression is going to be equal to 0, so I can rewrite this expression like this: B sine of theta to be equal to S sine of theta S. So this is going to be equation number 2. Now, using these two expressions, number 1 and 2, you can then find out the other expressions that we wanted to do in the problem statement. Another problem that you can identify in these two expressions is that uh, what is the nature of this theta s over here? So this is something like a question mark for us. Uh, I would invite you to make some physical sense of the mechanism. And that would be something like you visualize how the hydraulic actuator is going to extend itself. So when this extends, it means that the S is known to me, or I can readily identify using some sensor that what is the extent of extension or retraction in this particular case. So, so for that reason, S is something which I can readily identify. But theta is the angular displacement because of this particular hydraulic actuator to be pivoted over here is going to be not that straightforward unless you specify some special sensors like encoders over there. So in normal form, this is not going to be something related readily with the extent of or the kind of movement that we are going to have. So this theta s is not readily available. So I would indicate that not readily available. So can we eliminate that? So that is going to be the question over here. Can we eliminate it? Yes, we can, and this is exactly what we are going to do in the next slide. So I'll write down these expressions 1 and 2 over here, and I'll take these squares on both the sides. So this would be something like you have B cos of theta minus L whole thing squared to be equal to S cos of theta S squared as well. So this is corresponding to equation 1, and I can write down like that. Equation 1 implies that, and equation 2 similarly implies that I can write down expression like B sine of theta whole squared to be equal to S sine of theta S squared. And then obviously I can add them together. So this addition is going to result in on one side having S squared taken common, and then you have cos square of theta s plus sine square of theta s, which obviously you can understand that this is going to be equal to 1. But on the other side, you can write down like this expression, like you have B cos of theta minus L squared added with B squared sine squared of theta. So I'll expand this expression further. So this is going to be equal to B squared cos squared of theta plus L squared minus 2BL cos of theta on one side plus B squared sine squared of theta to be equal to S squared. So now you can readily identify that you have B squared cos squared term over here and B squared with the same, you can take common from the two, and you'll have the sine square theta in term in there, which obviously is going to reduce to be equal to 1. So this is going to result in like B squared plus L squared minus 2BL cos of theta to be equal to S squared. So I'll label this particular expression as expression number 3, and we're going to make use of it later on. So at this particular stage, it would be advisable to see that like you have the expression to identify how the S is changing and what are going to be the effects corresponding to the mechanism that we have drawn already. So now at this particular stage, what I'm going to do is to take the time derivative d by dt of this whole expression, and that would be something like, I'll write it down like this, like you have 2b dot term over there, and obviously b, since b is constant, so this is going to be equal to 0, and similarly you have 2l dot term, which is also going to be equal to 0 because L is not changing with time, and then you have minus 2BL cos of theta can be taken derivative of, and that is going to be something like sine of theta with a positive sign now over here dot theta dot is equal to 2s dot. Now over here S is changing with time, so that's why S dot term is going to remain there. It is not going to be equal to 0. So with this realization that now you have got this expression taken the time derivative of, you can write down the expression for S dot term over here. So this would mean that S dot is equal to, you have this whole term on the other side, 2BL sine of theta, and I'm going to write down theta dot momentarily over here divided by 2s. So this 2 can be cancelled with this, and I can write down this term in a bit of nicer form, like BL over s theta dot sine of theta. So this expression over here is indicating how length is changing with time, corresponding to the hydraulic actuator identified with the S dot. Now this would mean that S dot is an expression that I've already computed. So this is equal to BL over S theta dot sine of theta. So I'll kind of encapsulate it. So this is one of the expressions. But now I need to identify, because the problem statement was indicating that I must know how the height is changing with time. So this h, or h dot to be precise, the rate with which the h is changing, is going to be an important aspect. So let me indicate that over here. So this height from this point all the way to this is going to be important, and then the h dot corresponding to it is also going to be important. So I need to identify that, and for that reason I need to redraw another once more the mechanism, and let me quickly do that. So this is going to be something like you have this triangle over here. The same triangle is redrawn, but now you have the extension of the mechanism also indicated over here. So this whole length is going to be 2b, and corresponding to h, I would say that this is the height h. So now you can identify that if this total length 2b is known to me, I can readily identify the expression for h that is going to be equal to 2b sine of theta over here. So when you have this expression for h already known, I can make use of it over here to identify expression for h dot, which is going to be equal to 2b theta dot, and then you have cos of theta over here. So this is going to be the other expression. So now you can see that the expression for s dot is known to me, and expression for h dot is already available over here. But in these two expressions, you can readily see that theta dot term is appearing in both sides, or in other words, the rate with which the theta is changing. So I need to eliminate this as well in order to have the expression in the nicer form. So since I've got these two expressions already with me, so I'm going to find the expressions eliminated after eliminating the theta dot term in it. So h dot can be rewritten like this, like you have theta dot. This would mean that theta dot is equal to h dot over 2b cos of theta. So plug this value back to s dot expression. So putting this in s dot expression, so this would mean that s dot is equal to bl over s, and then this whole expression h dot over 2b cos of theta times the sine of theta. Now you can readily see that you can simplify it a little bit. So this would mean that s dot is equal to h dot l over 2s, and then you have sine of theta over cos of theta. This would mean that I can write down tan of theta over here. So now this expression that we have now found out is where you can readily see that there is no theta dot term in it. So that is going to be an expression that we can use, and we can further kind of elaborate this expression if we plug in the value corresponding to s over here. So remember, we computed previously the expression for s square previously in previous slides. So I can plug in that value over here to find out that. So recall, I'll use this space over here. Recall that that expression was something like, if I remember correctly, s squared to be equal to l square plus b minus 2lb cos of theta, something like that. So you know that you have s squared term already known, so you can take the square root on both the sides and find out the expression for s. This would mean that I can plug this value into the expression for s dot. This would mean that s dot is going to be equal to h dot l over 2 into under root of this whole expression like this, like you have l squared plus, this was b squared, I suppose, b squared minus 2lb cos of theta. So this is going to be one part, and since you have tan of theta as well, so that is going to be written on over here. So this expression is a nicer expression which correlates, or which connects the change in the hydraulic actuator defined in terms of s dot to be related with how the height is changing with time. So this is for the hydraulic actuator, and this is for the car height. All right, so this is the expression that we wanted to find out to solve the problem that we identified earlier. Now, since we have to plug in specific values corresponding to L, uh, uh, B, and for specific theta angle as well, so we are going to do that in the next slide. Now, for the case where specific values were given, we need to use this expression for S dot to find out how the H dot was changing. So specifically, it was something like length was given to be equal to 2b, which was equal to 2 meters, which would mean that b is equal to 1 meter. And there was something like S dot given to be 1 meter per second, and theta was, to be precise, 30 degrees available. So when you plug in these values over here, you can readily see that theta is already given over here. Length I already know. B is known. And S dot is known. So I can readily find out H dot term. So this would mean that I can simply plug in these values in, and this would turn out to be something like 2.1466 meters per second. So kindly counter check that whether this one is correct or not, but it is just like plugging in the values over here. So in this particular problem, it would be advisable now to identify what we have done. We have followed the procedure in a very simple, straightforward manner. First of all, we realized that what was the mechanism, made some sense of it, that how physically the things are going to change or manifest themselves. And then using the vector loop equations, we constructed one diagram. And from that set of vector loop equation, we found out the generic expression corresponding to S dot. And once that S dot is known to us, eliminating all the unknowns or all the parameters or values which are not readily available, we found out this expression which we can readily use to identify for some specific values, uh, uh, some specific results corresponding to those. So this is exactly what is going to be repeated even in exams as well. You will be given one problem. You will be asked to identify what are going to be the expressions, the generic expressions corresponding to those. And once those generic expressions have been found out, you can plug in the values to see what are going to be the specific results corresponding to a specific set of given data. So this is just like to give you some insights how you expect these problems to be there in your exams as well. The second problem that I've selected today belongs to agricultural applications. In agriculture, you would find quite a few number of interesting mechanisms which are attached to tractors, uh, primarily sometimes to prepare the fields, to sow the seeds, and to harvest the crops. And you would find that in most of these applications, in most of these mechanisms, they use the hydraulic system of a tractor to engage the powered action. And you can see that hydraulic system over here. Uh, Hydraulic system is going to produce the power, obviously, and that power is needed to be transmitted or transferred in a specific way, and that is done generally using mechanisms. And on the rear side of this tractor, you can see that mechanism at display. So in this particular application, what we're going to do is to use the vector loop equations or analytical approach to find out the equations, the kinematic equations over here. And then we're going to determine velocities of the mechanisms when some input is provided from the hydraulic system. So this is the task in hand. We are going to proceed from the next slides to try to solve this problem. The very first step that I'll take over here is try to draw a schematic illustration on top of this actual diagram. And the aim is to reveal the mechanism through line drawing. So I'm going to start from a node over here. this node, you can see that it's kind of a ground node. So I'll indicate something like this over here. And then you can obviously see that the link which is connected to this ground link has got 1, 2, and 3 nodes connected to it. So it is not a binary link, it is a ternary link. And for that reason, I can connect this point with this point, this node with this third node, and the first one with the third one. So you can see that you have this triangle exhibiting a ternary link. Then you can see that this node over here, the lower one, is connected through another link down here up to this point. Now, one thing that is different in this particular link is that you can obviously see a hydraulic actuator over here, so which means that this link has got the extendability in it, so which means that it is a prismatic joint, to be precise. Now over here you can see the lower node down here is also a ground node, which means that actually these two nodes are or can be considered as part of the ground link. Now interestingly, if you go further downwards, you can see another node right over here, which is also another ground node, so you can extend the ground link down there as well. Now this particular node, which is the last node vertically, is connected with a link which goes out of the system up to this point, where you have another node right over here at the far end. But in between you can see another node right over here which is connected with another link, which if I can try to draw drawing a straight line, this would something like this. So which means that you have a complex linkage mechanism at the rear side of this tractor, which is going to be governed by the hydraulic actuator, forcing these extended links to drop down and upwards, thus making the tractor plow the fields or prepare the fields accordingly. So this is a very interesting application, because you can see a complex linkage mechanism at display right over here as we've drawn it. If I view this mechanism from sight, I can redraw the whole schematic on the empty side of the slide, and that would look something like this. You have this node connected with a ternary link, something of this shape. And in order to make this like a single ternary link, I'm going to hatch this. Now over here I can draw a straight line just to indicate the ground link, and you have another node right over here grounded. Now what happens is that you connect this with a prismatic joint with the upper node over here. So I'm going to try to draw a straight line, something like this. Just to kind of illustrate the extendable link over here. Now another ground node is appearing right over here as well. So I'm going to show that as well. And I'll extend something like a link outwards, where you have the extended node there as well. But the upper node from this ternary link goes or drops down here in this fashion and connects itself over here. So in this particular scenario, you can see that the line diagram matches or appears similar to the one that we have drawn right on the diagram. So at this particular stage, it would also be advisable to label these links so that we can use this notation for the subsequent computation. So I'm going to start from the ground link. So I can label this one as R1. And the one that is the second link can be labeled as R2. And now the issue with this is, like, you have one vector starting from here. Let me use a different color over here. So this vector starts from here, it goes all the way to this, but on the same link you have another vector coming in right over here all the way to this, which is also going to belong to the second link. So I should have some sort of notation which differentiates the two. So this R2 should be different from the R2 up there. So what I'm going to do now, I'm going to say that this is R2A, the first part of it, and this is R2B. Now similarly on the ground link, you can also observe that ground link is not something like straightforward. You can start from here and you can go all the way up to this point, and that would be somewhat different from if you start from, let's say, over here and go all the way to this point over here. So this R1 can be labeled as R1A, and I can label this one as R1B to differentiate the two. And then obviously there is this another link which is R3 over here, and I can label this one as R4, this as R5. Now on this line diagram, you can very easily see that you have multiple links, and the notation is quite visible. So what is going to be the path taken in order to kind of write the vector loop equation for this mechanism? And I can think about that, and I can kind of visualize the whole system and see the internal nature of it or working of it. And what is like very visible for me over here is that I can differentiate like two 4-bar mechanisms at display right over here on this diagram. So the very first one, and let me use a highlighter over here, the very first one is going to be a 4-bar mechanism which is from here to here and this, and if I draw vertically something like that. So this is a 4-bar mechanism that I can see, and I can kind of convince myself that since I've kind of solved this one or similar 4-bar mechanisms multiple times, so it would not be a very difficult task for me to develop the vector loop equations. But since it is not kind of completing the story, I should realize that there should be something like an additional mechanism as well. And I can see that another one, let me use a different color to highlight that. There is this mechanism over here, or this linkage over here, which is kind of also appearing in the same scenario. And when you have two mechanisms, and actually in true sense these are not independent from each other, there must be some sort of constraint equations which are going to define how these two are interrelated with each other. So that's why I should try to develop very simple, straightforward equations. One equation is going to be corresponding to this color, the other one would correspond to this color, and I'm going to write a constraint equation corresponding to this color. So let's quickly try to write down those equations. So the very first one corresponding to green is going to be an equation which says that R 1a plus r2a plus r3 plus r4 is going to be equal to 0. So this is one vector loop equation. The other vector loop equation can be corresponding to r1b. You can see that over here, plus r2b plus r5 to be equal to 0. The third one, which corresponds to the constraint equation, that is because of the ternary link placed over here. I can see that something like over here you have a fixed angular displacement, and this is the angular displacement that you can specify. So that would be something like you have a theta which is I should say 2b to be equal to theta 2a plus let it be like alpha 2. So I'm going to label this one as alpha 2, which means that the angular displacement corresponding to R2b is related with the angular displacement corresponding to R2a by having a fixed angular displacement between the two because of the ternary link that we have specified already. So you have now three equations over here which are going to define the internal working of this mechanism in the subsequent slides. So now we have the schematic diagram of the mechanism over here, and we know the set of basic equations. The very first one corresponds to the linkage number 1, let it be like L1. The second one corresponds to the linkage number 2, let it be L2. And then you have the constraint equation, which I can label it to be like C. Just a little correction, I've just realized that this should be a minus sign over here. So with this realization that you have got the three equations known to you, now once again you have to kind of see what was the original problem. The problem is to find out velocities. And velocities have been selected because if you know the procedure for velocities, you can obviously move one step further to find out accelerations as well. So the procedure is not going to change. So that's why velocities is going to kind of cover all the basics that we wanted to cover over here. So for velocities, I can identify that I need to have theta 2a dot known. I need to compute theta 2b dot as well, and then similarly theta 3 dot, theta 4 dot as well, and then you have theta 5 dot as well. So I need to compute that, and these correspond to linkage in the linkage link number 2, which is a ternary link, link number 3, 4, and 5, and these are needed to be known, obviously. So we need to compute these, and what is known to us is R5 dot, if I may say that. So this corresponds to the hydraulic actuator, how this is going to impart a velocity as the input to the whole mechanism. So this is what we already know. So this is the input, and because of input it is known. So you need to kind of realize that what is the original problem in hand. So now you have got these three equations. You know what is needed to be computed, and you know what is already known to you as input. So these, from this starting point, we can start our journey. So the very first thing that we need to do over here is to take equation L1 and try to take the derivative of it. So I'm going to do that by taking the time derivative of this expression. And while doing that, I would automatically convert this equation into a polar form as well. So this is going to be something like d by dt of L1, which is going to be equal to R1A dot e raised to power j theta 1a plus the same one R1a, then you have theta 1a dot j e raised to power j theta 1a. So this is actually a time derivative of the expression R1a e raised to power j theta 1a. And I've kind of illustrated both the components of it, assuming that sometimes R1a is going to have a variability imparted into it, as is the case corresponding to R5. So in order to kind of make this point eventually for R5, I've kind of included it over here for the sake of completion. And then you can add with the next term, which is R2a. This is going to be R2a dot e raised to power j theta 2a plus R2a theta 2a dot j e raised to power j theta 2a. So this whole is going to be the time derivative of R2a e raised to power j theta 2a. Then you need to add this with the third term, which is corresponding to R3. So this is going to be, I'll try to quickly do that, R3a dot e raised to power j theta 3. Not the, there is no a part in it, so I can erase that. Add it with R3 theta 3 dot j e raised to power j theta 3. Then you add this with R4 term, which is going to be R4 dot e raised to power j theta 4 plus R4 theta 4 dot j e raised to power j theta 4. And obviously you can see similarly both the terms corresponding to time derivative of R3 and R4 in the expression L1. Now you can readily see that in your case, let me use a different color, R1a dot, which means that rate of change of R1a, which obviously you can see is a fixed ground length. So this is going to be equal to 0. So that's why it is going to be accounted for. Similarly, since theta 1a is also fixed, it is going to be not changing. In this case, it would remain 0. So it would mean that this term is also going to be equal to 0. So this whole expression over here corresponding to R1a, the ground length, is not going to have any role to play when you take the time derivative. And similarly over here you can see R2a dot, which is the rate of change of 2a, which is not going to change because it is a fixed rigid length. So this is going to be equal to 0. Similarly, R3 dot is also going to be equal to 0. And R4 dot is also going to be equal to 0. So obviously, as a result of this whole kind of rearrangement, I can write down, let me use the same color. So this is going to be equal to R2a theta 2a dot j e raised to power j theta 2a added with r3 theta 3 dot j e raised to power j theta 3 added with r4 is going to be theta 4 dot j e raised to power j theta 4, and this is going to be equal to 0 uh, in this scenario as well, because this was already equal to 0 over here. So now you have got an expression which is in a polar form, and now obviously I can use the Euler notation to subdivide this into a real and an imaginary part, and that I'm going to do in the next slide. Now, using the Euler notation, I'll say that the real part is going to be from the previous equation. This is going to be minus r2a, then you have theta 2a dot sine of theta 2a, then you have minus r3 theta 3 dot sine of theta 3, and then minus r4 theta 4 dot sine of theta 4. So this minus sign appears because j multiplied with the j of the Euler notation, so this is going to be minus 1 because of that. The imaginary part is similarly going to be equal to r2a theta 2a dot cos of theta 2a plus r3 theta 3 dot cos of theta 3, then you have added with that r4 theta 4 dot cos of theta 4. So these are going to be the two equations coming in by differentiating L1 equation with time. And similarly, you can do the exercise for L2 as well, and this would mean, so let me make a little division over here. For L2 expression, after taking the time derivative, you are going to find out like this: d by dt of L2 is going to be equal to something using the Euler notation and the polar form. This is going to be r1b dot e raised to power j theta 1b plus r1b theta 1b dot j e raised to power j theta 1b, and these were the two terms that we have previously mentioned as well while doing the other exercise. Then you have the second term over here, which is going to be added with r2b dot e raised to power j theta 2b added with r2b theta 2b dot j e raised to power j theta 2b. So these are the two terms corresponding to when you take the time derivative of r2b. This corresponds to when you take the time derivative of r1b. Then you have to add that with r5 term taken time derivative of, and this corresponds to r5 dot e raised to power j theta 5 plus r5 times theta 5 dot j e raised to power j theta 5. So this corresponds to when you take the time derivative of this last term over here of R5, and this whole is going to be equal to 0. Now you can readily identify that R1b is not changing with time, so that's why let me use consistent colors over here. So this is going to be equal to 0, and then you have theta 1 2 dot also not changing with time, so this is also going to be equal to 0. And then you have obviously R2b, which is also not changing with time, so this turns out to be equal to 0. And interestingly, R5 dot is going to have a change imparted because of the nature of the joint over here. So this can extend or this can retract because this is the hydraulic actuator of the tractor. So that's why it is going to be the input element. So R5 dot is actually input given to the system. So that's going to be there and having an effect. But over here, theta 5 dot can be something like we need to see that how this one is going to have uh, a change imparted because of the extension of the hydraulic actuator. So that would be an interesting observation to see how theta 5 dot is going to change, is going to take effect. So with this realization that you have got a few terms taken out of the system, you can once again write down this expression. I'll use the same color. So this is going to be equal to something like R2b theta 2b dot j e raised to power j theta 2b added with the R5 dot term, which is interesting in itself, e raised to power j theta 5. Then you have R5 theta 5 dot j e raised to power j theta 5, and that is going to be equal to 0. Now you have this expression which is appearing because of taking the time derivative of expression L2. So this is what we're going to use in the next slide in a similar case that we have done in case of expression for the L1. So using the Euler notation in a similar fashion, for the previous equation, we can say that the real part is going to be equal to minus R2b theta 2b dot e raised to power, sorry, because we have used the Euler notation, this should be sine of theta 2b added with R5 dot term, but now we have with cos of theta 5, because this is the way it is going to appear, because there was no j involved in it, minus R5 theta 5 dot, then you have sine of theta 5, and this is going to be equal to 0. And similarly the imaginary part is going to be constructed in a similar fashion. This is going to be R2b theta 2b dot, then you have cos of theta 2b added with R5 dot term, but now over here you have the sine of theta 5, then you have added with that R5 theta 5 dot cos of theta 5 to be equal to 0. Now in this fashion we have covered L1 and L2, and now we have to cover the constraint equation. So if we take that, now the constraint equation, and this when taken the time derivative of, this would mean that you have d by dt of constraint equation, which is going to be time derivative of theta 2b to be equal to theta 2a minus alpha alpha 2, and this alpha is because it is constant because of the nature of the ternary link, because you have this one as the solid portion. So for that reason, you can simply write down like this, like you have theta 2b dot is equal to theta 2a dot minus 0. So as a result of that, I can write down this equation to be minus theta 2a dot plus theta 2b dot to be consistent with the upper expressions to be equal to 0. So this expression is going to be used in addition to the 4 expressions that we have mentioned, 2 over here and the 2 in the previous slide. So in that particular scenario, you can see that you have 5 equations in hand. So I can count that how many unknowns are there. I can see that in terms of velocity, these were, if I make you recall, theta 1b, sorry, theta 2b dot, and then theta 2a dot, theta 3 dot, theta 4 dot, and theta 5 dot were the 5 unknowns uh, that we wanted to solve. So 5 equations, 5 unknowns, we can handle this whole scenario. So this is what we're going to construct in the next slide. Let's go there. Since I have 5 unknowns and 5 equations for those, it would be very difficult for me to solve like in the conventional method as we have done previously. So it would be advisable over here to make use of the matrix notation, and that is going to help us quickly solve the expressions using even the analytical tools as well as the computer tools as well. Uh, so so I'm going to construct these 5 equations in that form, and I'll ask you to kind of write a little program for that in order to solve simultaneously those 5 equations for 5 unknowns. So let me kind of construct that set of equations. So this is going to be in a matrix form, constructed something like that, like you have a matrix A, uh, so that multiplied with the velocities over here, joint velocities, if I may say that. So let it be like AV, that is going to be equal to the input velocities given to it. So if we can construct this whole scenario in this structure, that would be great. So for that reason, I'll have a big matrix A constructed. Let it be like this is the space for that. Um, and then you have V, which is going to be actually the unknowns that we have to solve these equations for. So that is going to be in the way we have constructed them, theta 2a dot, theta 2b dot, if I can write down theta 3 dot over here, theta 4 dot, and theta 5 dot. So that is going to be equal to the inputs given to the system. So that is constructed like a vector over here. So we can observe these 5 equations and write down those coefficients over here. The coefficient corresponding to theta 2a dot is going to be written like over here. So let me kind of subdivide this whole scenario into 5 columns. 2, 3, 4, and 5. So this corresponds to theta 2a dot term over here. So this, for the very first equation, this turns out to be minus r2a, and because we have confined space, I can use a short notation, and generally in robotics we do use these kind of short notations. So this is going to be sine, this is going to be sine of theta 2a. So this is kind of a shorter version of saying that this is going to be sine of theta 2a, just for the sake of brevity we have used that. So this is going to be 0 over. There is no theta 2b dot term in that. There is obviously theta 3 dot term over there that was corresponding to minus r3 sine of theta 3, and then you have minus r4 sine of theta 4 in there, and there is no theta 5 dot term in there. So that's the first equation, and that was equal to 0. So you can write down in a similar fashion the other four equations. I'll quickly write down those. So the second equation turns out to be r2a cos of theta 2a. Then you have 0 over here, r3 cos of theta 3. Then r4 cos of theta 4. And then you have 0 to be equal to 0, and then you have over here 0 minus r2b sine of theta 2b, 0 0 minus r5 sine of theta 5 to be equal to, now in this particular case you are providing input in terms of this displacement over here, so that's why it is on this side. So this is minus r5 dot c5, because we have taken the term on the other side of the equation, so that's why it is with a minus sign. Similarly over here you can write down quickly the fourth equation. This is going to be r2b cos of theta 2b. Then you have 0 0 r5 cos of theta 5, and on the other side you are going to have minus r5 dot cos of uh, 5. I'll counter check that because I suppose that it should be something like different. So this is going to be minus 1 0 0 0 and 0. This should be equal to 1 because this is r theta 2b minus theta 2a. So this should be equal to 1, obviously. So kindly do make a little correction over there. All right, so let me counter check this term. Yes, this would be not cos of theta 5, this should be sine of theta 5. Let me use a sine notation. So in this fashion you can see that you have got the expression, all the five expressions written in terms of a matrix A multiplied with the vector which we need to solve for the unknowns. This is V and this is what is given to it, like the input. So now since you have got this as the set of equations, you can obviously solve for V to be equal to A inverse of B. When you solve this equation, take this whole big matrix on the other side by taking inverse of it. This you can do using MATLAB or Python, and you can find out the unknowns, the 5 unknowns that we have listed: theta 2a dot, 2b dot, theta 3 dot, theta 4 dot, and theta 5 dot. So these are going to be the unknowns solved when you solve this expression. So in this fashion, you have started by observing the actual figure, drawing the schematic line diagram out of that, similar to this, and afterwards you were able to see that how this diagram can be translated eventually in terms of a set of equations. So you did that, and from here you took the time derivative, constructed the vector loop equations in the polar form, and then you translated those into Euler notation, separated the real and imaginary part from each other, and then you constructed 5 equations using that, 5 equations for 5 unknowns, and because it was kind of a laborious task to simultaneously solve those, so we have constructed this matrix notation over here to use the principles of linear algebra to solve uh, these equations for 5 unknowns. So once you're going to solve these, you're going to get all these unknowns, and that is going to give you the realization of how the joint velocities are taking shape when you provide input in terms of hydraulic actuators driven by the hydraulic pump. So this is it for this particular problem. We have solved it. At this particular stage, we can feel very confident that we have solved two problems in detail. These problems were different from the problems given in the book. So this is going to give you some additional confidence that you're not kind of victim to the end problems given in the book. You can solve something out of that conventional ambit as well. So by doing that, you can realize that how the thinking process should be constructed in order to find out the appropriate solutions. So I would advise that you should also solve the end chapter problems, and you should also try to consult other sources to develop a practice so that you can in exam solve these problems efficiently in a short time. But having said that, it is also important to realize that uh, the solution is also dependent on how good you are in actually realizing the working principle of the mechanism shown. So whenever there is something like a figure or diagram flashed in front of you, you should be able to try to identify uh, uh, using the techniques that we have studied in previous sessions as well, to identify what is going to be the working principle, what is the physical sense of that movement exhibited by that particular mechanism. So if you develop that skill, that expertise by observing these mechanisms, you would be able to address any problem given in the exam. So this particular session was specifically arranged in order to make you feel confident about the kinematic analysis that we have spent much time on it. A few students said that it would be advisable, it is recommended that uh, this kind of session be arranged. So that's why I've arranged this session. So if you have any queries, any questions corresponding to the problems solved today, you can obviously place comments in the Microsoft Teams folder. I'll respond to those at the earliest, but I feel confident that you have now covered quite a few bases. So you have all the requisite tools already available with you. You can solve any problems given to you in the exams. So this is it for today. So next week we are going to start doing the geared mechanisms. So be prepared for that. Until then, bye bye.